Alright, so in this video I'm going to look at rates of reactions, and in particular I'm going to look at the order of different reactants. So to do that, I've just got a generic chemical equation here. I'm reacting A and B and C, and I'm trying to make D. And when we're looking at the rate of the reaction, we're looking at how quickly those reactants are being converted into products. And at GCSE, when you looked at rate, you learned that if you increase the concentration of a reactant, you will speed up the reaction. So for example, if I increased the concentration of A, I would expect the reaction to get faster. And the reason for this is if you've got a greater concentration of A, you've got more particles in your flask, therefore you've got more frequent collisions. But when we look at rates at A level, we see that it's slightly more complicated than that. We'll see that some reactants, that their concentration doesn't affect the rate at all. We'll see that for other reactants, their concentration has a large effect on the rate of the reaction. And this is called the order of a reaction, and it's what we're going to look at now. So what I'm going to do is I'm going to do, zoom in this a little bit. I've got mock results here for an experiment. So I'm saying that in my first experiment, my concentration of A is 0.1 moles per decimeters cubed. This is my concentration of B, this is my concentration of C, and I measure the rate and I find that this is the rate of the reaction. I want to see how changing the concentration of A affects the rate of my overall reaction. And because I'm interested in A, I'm going to change A, but I'm going to keep B and C constant. So I'm going to I'm going to start by doubling A. So I'm going to go from 0.1 moles per decimeters cubed to 0.2 moles per decimeters cubed. And because I'm interested in A, I'm going to keep B constant, and I'm going to keep C constant. And then I'm going to look and see what effect that has on my rate. And let's just say it's got no effect on my rate whatsoever. My rate of reaction is still 2 moles per decimeters cubed per second. If changing the concentration of A has no effect on the rate of the reaction, then I can say that A is zero order. And that means it doesn't matter what I do to the concentration of A, the rate is not going to change. I could halve the concentration of A and the rate wouldn't slow down. I could double the concentration of A, triple the concentration of A, even increase the concentration by a factor of 10, and the rate is not going to increase. Now I'm interested in B, so I'm going to do a third experiment, and in experiment 3, because I'm interested in B, I'm going to keep A and C the same, but B I'm going to double. I'm going to go from 0.1 to 0.2, and I'm going to measure the rate of my reaction. I'm going to see what happens. And in this case, I see that the rate increases from 2 moles per decimeters cubed to 4 moles per decimeters cubed. So I've doubled the concentration of B, and I've also doubled the rate of my reaction. And for B, then, I can say that it is first order. And that means whatever I do to the concentration of B, the same thing will happen to the rate. If I triple the concentration of B, I will triple the rate. If I half the concentration of B, I will half the rate. Next, what I'm going to look at is C. Again, because I'm looking at C, I'm going to keep A constant, I'm going to keep B constant, so they're back to what they were in experiment 1, but C I'm going to change, and again I'm going to double C, and I'm going to go to 0.2, and this time I see that my rate increases all the way up to 8 mole per decimeters cubed per second, so there's a big jump in the rate this time. I see that if I double my concentration of C, my rate increases by a factor of 4. So 2 multiplied by 4 is 8, so my rate is increasing by a factor of 4. And in this case, I can say that C is second order, okay? And the reason it's second order is I have doubled my rate, but my rate has increased by a factor of 4. So my rate has increased by a factor of 2 squared. And the fact that it's increasing by 2 squared, the squared here, tells me that it's second order. I'll do a few other examples with the second order just so you can see exactly what's happening. Again, I'm going to keep my A and B constant, and C, instead of doubling it this time, I'm going to triple it. I'm going to go from 0.1 all the way up to 0.3. And what I see happens to my rate this time is that it goes from 2 all the way up to 18. Okay, so this time I've tripled my concentration, so I've got 3. And my rate is increasing by a factor of 9. So 2 times 9 is 18. It's increasing by a factor of 9. which again is 3 squared. So it's second order, so it's 3. I've tripled it to the power of 2 because it's second order. If I were to quadruple it, go from 0.1 all the way up to 0.4, I'm quadrupling the rate, so it's 4 to the power of 2 because it's second order. 4 squared is 16. I would expect my rate to increase by a factor of 16. It starts at 2. Increasing by a factor of 16 would give me an overall rate of 32 moles per decimeters cubed per second. So what this is showing me is that if I'm doing this reaction and I want to increase the rate, there's no point in changing the concentration of A. The concentration of A does not affect my rate. But if I change the concentration of B or C, I will affect the rate, and in particular, any changes I make to C, because it's second order, is going to have a big effect on the rate of my reaction. And once you know the orders of your reactants, and you can only work that out experimentally, so just so we're clear, if I had a reaction, magnesium, if I were to react it with, let's say, hydrochloric acid, and I form magnesium chloride, and I form hydrogen gas, so balance that there. My balanced symbol equation does not tell me the order with respect to the reactant. So I can't look at HCl and say, oh, there's a big 2 in front of it, therefore it's second order. That's not how it works. To work out the order, I have to do the experiment multiple times, changing each concentration individually and seeing what effect that has on the rate. And once I've done that experimentally, I can then work out the individual orders, and then I can write what's called a rate equation. So my rate equation is rate equals K, which is the rate constant, which I will come back to, times the concentration of A to the power of its order. Now we said A was 0 order, so it's going to be A to the power of 0 times the concentration of B to the power of its order, B was first order, times the concentration of C to the power of its order, which we said was second order. I can simplify this because anything to the power of 0 is 1. So I can get rid of that from the equation completely because A to the power of 0 is 1. Also, when I'm writing my B, I don't need to write the power of 1, so I can leave that out. And then I can write C squared. And that is my rate equation. Now this here, K, is a rate constant. I'm going to come back to K in a separate video, and I'll talk about K in more detail. But for now, this is my rate equation, and I'm able to write it because I've worked out the order with respect to A, B, and C. The other thing you can be asked is they can ask you what the total order is. And for that, you just add up the individual orders. So I've got 0 plus 1 plus 2. The total order is 3. So we're going to do a few questions on this before we move on to the rate constant K. So bear with me a second. Here we go. So apologies for the glare. See if I can get rid of that. Kind of. So we're going to have a look at a few of these questions and then we'll move on. Where's my little pen? Oh gosh, that's really... So I've got a reaction here where I've given you the rate equation and I want to know the following. The first thing I want to know is state the order with respect to A, B, and C. There we go. So A is not in my equation. The reason it's not in my equation is because it's a 0 order. I don't need it in the rate equation because it doesn't affect the rate, and anything to the power of 0 is 1, so it just disappears. What's the order with respect to B? Well, B is raised to the power of 2, and that tells me it's second order with respect to B. What's it with power of C? Sorry, with respect to C, it's a first order because it's just to the power of 1. Determine the overall order. I've got 0 plus 2 plus 1. The overall order is 3. What is the effect on the rate if I double the concentration of, if I double the concentration of A? I've said that A is 0 order. That means changing the concentration has no effect on the rate. So I can just write that it has got no effect. If I double the concentration of B, B is second order. So if I double, it's 2 to the power of 2. My rate is going to increase by a factor of 4. What is the effect if I double the concentration of C? Well, C is first order, so whatever I do to the concentration, I also do to the rate. If I double the concentration, I double the rate, so I increase by a factor of 2. What is the effect of doubling all 3 concentrations at the same time? Well, with A, it had no effect. With B, it increased by a factor of 4. With C, it increased by a factor of 2. So I've got 4 times 2, overall it's going to increase by a factor of 8. What I want you to do now is pause the video and have a go at the questions here below, which are the same. So pause, do these ones for yourself, and then press play when you are ready to go through the answers. So I've filled in the first two, which should hopefully be straightforward. I'm going to pick up here on C. So what is the effect on the rate of increasing the concentration of A by a factor of 4? I've said A is second order. If I'm increasing by a factor of 4, it's 4 to the power of 2. The rate is going to increase by a factor of 16. The next one, what is the effect on the rate if I halve the concentration of B? Well, B is first order. If I halve the concentration, I am also going to halve the rate. What is the effect if I halve the concentration of C? Well, C is second. Sorry, I accidentally paused that. Whatever I do to the concentration of C, I'm going to be squaring it. So if I halve the concentration, it's going to be a half squared, which is going to be a quarter. So if I halve the concentration of C, my rate will decrease by a quarter. What is the effect if I double all three concentrations at the same time? If I double the concentration of A, so A is second order, and if I double the concentration, it's going to increase by a factor of 4. B, we said, is first order, so that means it's going to increase by a factor of 2. And C, we also said, was second order, which means it will also increase by a factor of 4. So I've got 4 times 2 is 8. 8 times 4 is 32. The rate will increase by a factor of 32. So if we have a look here, just pause that there and have a go at 3 and have a go at 4, and then I'm going to run through the answers. Okay, so I'm going to run through these answers. It's written slightly different. The order with respect to A, so it says if I double the concentration of A, I increase the rate by a factor of 2. So if I've doubled and it increased by a factor of 2, then A must be first order. I'm doubling and I'm increasing by a factor of 2. For B, it says if I change the concentration, there's no effect. That means it must be 0 order. And for C, if I halve the concentration, it decreases the rate to half. So again, that's first order. I'm halving the concentration, I'm halving the rate. The overall order is going to be 2. 1 and 1 is 2. The rate equation is then going to be rate equals K. The concentration of A, we said was first order. I don't need to put the 1. B, I can leave out completely because it's 0 order, and then I've got C, which is also first order, and I don't need to write the 1. The next one here, 3 reactants. Tripling the concentration of A increases the rate by a factor of 9. So it's 3 is to the power of 2 is 9. That makes A second order. If I double B, I double the rate. That makes B first order. If I half C, it has no effect. That makes it 0 order. 2 and 1 is 3. And determine the rate equation is going to be rate equals K. A we said is second, so it's going to be A squared. B we said is first, so it's going to be B. And C I can leave out of the rate equation because it is 0 order. In the next video we are going to have a look at K. We're going to look at what it is, where it comes from, why it's useful, and also how to calculate the units of K.